So from the last time where I showed the logic behind the contrastive loss. So these are deep metric models. This is not specific to contrastive loss. There are other methods that can achieve the same result. Okay, so it's loading. So it's idea that you want to make the same class samples closer by some metric and the different class samples farther away by some metric. So before I just showed you that you can use this by the clustering methods and then matching the real and the predicted class overlap. And the other method is with the center of the class, center of the mass. There is also like radiuses and all sorts of methods that you can think of. But for this one, so we have like number of ways how to do this, and we'll do in one quick way today using one of the simplest ones. So just a second, so like that. So number one would be the one that we'll do today is so the z vector is then passed to L2 norm, and then we calculate the Euclidean distances. Euclidean. So my question is then, so my question is like in the chat, what would be the max distance between any two samples using this approach? So what would be the max distance using this approach between any two z vectors? Any two z vectors? Do you have any ideas? So if you have no ideas, you can type in minus plus, so that then I can help you out a little bit to understand this. And then I go quickly to some other ways how to do this. So Christopher is saying that if it's a norm, then it's 1. So the length of any z vector is actually 1 for unit sphere, but this is not the answer. So maybe somebody else have ideas. Meanwhile, I will start trying to draw it. So the idea is that we have this unit space, and we have some z vectors. So for example, in the beginning, the z vectors, whoa, it's so small. Why it's so small? Anyway, in the beginning, z vectors are all around place like that. So after we pass to the last fully connected layer in the model, but then we project them using the L2 norm on the unit sphere like this face. So I guess saying the diameter, that is correct, but you could say also more precisely what is the diameter, because we already know that. So yeah, that is 2, that is correct. So it will be projected on any place here on the sphere, and if we just look, the longest distance between any two vectors would be this diameter of this unit space. By the way, some of the models that report one of the best results, they actually don't work in the unit space of like with the unit vector size of 1. They work with larger spheres. So if you multiply this by some coefficient, some papers report that you get better results like later. So I think at some point I can explain also that part. That would be interesting, I think. So, but with regards to this one, so this is one very easy method. And then, for example, if we pass all of our samples, we can calculate the center of the mass of all of our samples. Of course, for example, in these areas where we have these clusters, we can calculate the center of the mass somewhere in the middle, and then we can calculate which of the samples is to which center of the mass the sampler is the closest one. So all of these orange samples are closest to this center of the mass, right? But we have one orange sample here also, and this one is not closest to the orange cluster, so we would classify this as a not correct class. So they would be classified as this class, the light blue one. And in this way we can somehow estimate how good is our deep metric model. By the way, the fun thing that I must emphasize is that these deep metric models can work also with a kind of zero few shot learning, few shot learning. So the idea is that in the train learning, in the test on validation datasets, it could have some samples that it never seen during the training, and it would still work if the model is good and the domain is close enough. So this is one method. Then the second method that I will give some of those methods for my students to do as a homework as well, but for others joining, hopefully that is informative and interesting. So then the other method would be to use the Z to the L2 norm. So the L2 norm is required because we want to have some kind of constraint for our loss function, so it don't fly into the infinity in this case. And then we could use the PCA whitening. I think so I was written in this tutorial, but probably in the next one we can implement together some of the PCA variations of the algorithms. So there are quite a few of them, but the idea is that you want to project your z vectors or latent vectors to some arbitrary hyperplane that contains the most variation of or deviations of all of the points in the dataset. So that means that you can reduce from 32 dimensions to, let's say, 3 dimensions or 4 dimensions or even 1 dimension. So if it's 1 dimension, then it's not actually PCA. But so, for example, from 32 dimensions to 3 dimensions, now you have a lot less dimensions. When you have a lot less dimensions, the k-means works much better. So then would be either Euclidean, or you can use some clustering. So that would be some other method how to calculate the accuracy. Then the third method could be just to use a z vector without any normalization, and then use the cosine distances. So the cosine distances, this is a cosine 1 minus cosine similarity, and if you know the cosine similarity, this is like an angle. So you actually can use the that equation to calculate with arc cosine the angle between any vectors, but in general that function is very useful because it has some very nice properties. Okay, so just a second. We'll drop in that function and then we'll move to the code. So what are the props of reducing dimensioning with PCA? Properties for dimension reduction is that the higher dimensions you have, the worse Euclidean distances work. So if you have, let's say, 32-dimensional space and you want to work with Euclidean distances, there is higher probability that those distances would be more similar to each other rather than if you have a lower dimensionality. And with lower dimensionality, you also kind of reduce the noise a little bit. So the cosine similarity is this equation, and you can easily see that you can calculate theta also out of that one, but normally you would not calculate, so you would have the cosine distance as 1 minus similarity, and this would go, just a second, and this would go from range 0 to 2, basically the same way as the unit space. Similarity, hopefully I wrote it correctly, so like that. And so this would be from 0 till 2, and the way how it works, actually, it's really nice that if you think about it, the angles means that you cannot go over 180, right? So for example, you have one vector and you have another vector, And for here you have some kind of, let's say, 30 degree angle, or you can convert it to cosine similarity to some scalar value. And then this angle, if it goes till 180, right? And then afterwards it goes back, so it starts going back, and it still will calculate always the closest angle. So if you would like to calculate some angle that you determine yourself, then you need also to know this cross product. But in this case, it's not necessary. So here, let's say this one or this one. So it always calculates the closest angle here, and basically this means that it will go from 0 to 2 and slowly back, and that way you kind of optimize a little bit your space, that it is the embeddings are distributed so they don't go just in infinity in some direction and then get projected on the this unit space. So hopefully, at least in some way, this makes sense. I just don't want to spend too much time on it right now. I want to go to the code, and then we can go, let's say, next workshop back to some PCA whitening techniques, clustering techniques, and then slowly move to more advanced deep metric learning models, because this is just very beginning. At the same time, I also want to leave time for Bruno, his really nice material for today. So I will go to the code now. So I will share. So I dropped in the chat the template. I will drop it, and again, if somebody came later, hopefully that link is ready. So now I will share my screen. Where is this Zoom thing? New share. So my screen of the code. Okay, this one is ready, hopefully. So my template is actually the same code that I wrote last time with you together with the loss function. So I did not actually remind you the loss function today. Maybe I should do that. Just a second. While you prepare your code for the last time, I will remind you the loss functions. So we are using the really basic contrastive loss with hard sample mining with regards to the batch. And this is something that comes all the way from LeCun's early work. This is really old loss function. This is, I think it's sometimes called ranking loss or something like that. Just a second. So let me share you those. So one way to write it down is in following way, and you can rewrite it also in two parts, as I showed you last time, using a little bit simplified way. So this little notation of these two lines with the plus sign, this is some modern adoption from the FaceNet, that they also use that same notation, and some other models. So this is basically the hinge or the relu or the max. So all of this is basically the same name of the same function. So it don't allow you to have, so it's like max 0 or x. So that part of the equation is that one. So it kind of so it wants to have that all of the negative samples are within the margin. So no negative samples are closer than m margin. So that's what it means actually. And as you see right now, the those vectors that you can get for those distances, so these are distances, positive distances and negative distances. For every call of the loss function, you must have two vectors. So actually it's even more than that, but basically you need to have some kind of anchor vector with a positive and anchor vector with a negative. And those z vectors, of course, you can get from your model. So your model is this encoder. So any z vector you can get from f, the model of the x of the parameterized theta. Just a second, we'll move to the code. I promise you that this will not be too long. So maybe, hopefully this is clear how you get all of these things. So you have just a very simple convolutional encoder. From the images you get the z vectors. You mine in your batch, you look for the samples in the batch that have the longest distances between the anchor and the positive ones, so these are dp's. So this is a Euclidean distance equation, so that basically you have the longest distance between those two, and the shortest distance between the negatives, and the negatives are the different class samples. If you pass like the one class sample and the other class sample, then that is a negative sample, and that one you don't want to be close. If it's a close, then this is a bad thing, so that's why you want to make it farther away. Okay, hopefully that is kind of giving a small picture of what it is, and now you can also read the same thing in the code. Basically, it's not something that it is only in the equation. We already made it actually. So now I'm sharing the code, and I will just add today this accuracy calculation part, and then for my students I will give also some extra tasks later. So let's do the accuracy part. Just a second, I will prepare my stuff. So here again, if you run this on your local computer, then it will probably it will not work properly, because so it depends on your local computer. So I made that the CUDA, if there is a GPU available, then it don't have any limits for your dataset. So if you have in your local computer a GPU and you just want to debug it, then I advise you to change this line maybe to 200 or whatever, or just comment it out. So, but if you don't have GPU and you want to run this on Google Colab, for example, then you can leave it as it is. And we'll move to this more important part. By the way, this tutorial will also be available as a video later, so at least my students can, and any interested in this can work a little bit like slower on this, but let's see if we can succeed working on this together. So one thing that we also want to track probably is the positive and negative distances and the accuracy. So if you look at our dictionary where I post all of my metrics that I want to track, I have already the accuracy. That last time we made all together this simple classification model. So this time we want to make sure that this works with the deep metric learning. So here, let's say we can also have the distance of the positive. So let's calculate the average distance of the positives and average distance of the negatives. So that means that we want to look at all of the distances between any z vectors, and think about, so we want to see that the positive distances are reducing and the negative distances are increasing probably. Yeah, so that would be nice. And to calculate that, we can go a little bit, scroll down. And by the way, if you have some questions, something not clear so far, you can try to ask some questions. So we aggregate the losses. So the losses is something that we do the hard mining. So I try to illustrate here with the small like ASCII images of the distances of the same class and different class, and trying to find the worst sample for the loss. Of course, you can try it also with all samples, but it might converge a little bit slower maybe. So this, so we can write down here, what was the name, how I wrote it? This, yeah, so we can calculate here, let's say vector, not vector, but array. Sorry for scrolling, I don't know why my scrolling is lagging a little bit. So this positives, this will be one vector, and the other vector will be negatives. By the way, I know some people who are attending the workshops saying that there are some tools where you can copy your screen using some picture-in-picture mode. That if you don't have two monitors, that's easy way for coding along with me. So, and I also will add these things to the Jamboard, so maybe that's also a good idea. So I will quickly add these things to the Jamboard as well. So, and we will quickly also add the calculation of the accuracy, and then I'll give the word to the Bruno. So just a second. and next time we can work on maybe the PCA and the clustering techniques. So if I copy this one and drop this to the Jamboard as well, so you can follow up with these few lines of changes. By the way, I found out that the students who follow these workshops and kind of just not copy ready-made code but try to write themselves tend to kind of remember it a little bit better. But I guess the same true if you have like all of these cool tools like Tab 9 or something that completes the code, or you write it yourself. If you write it yourself, you kind of understand it, like your brain works probably a little bit more intensively. Of course, maybe that's not the case for all of the situations. So here append torch mean, so we can calculate the mean of those distances that are the positives. So we can use, let's say, dists all, dists all. Oh no, there's no dists all, there's just dists. Okay, dists. So from these distances, I want to look at only where the y matches the yi. So these ones. And then I also want to have the detach. So detach would then make sure that there is no problems with gradient. So I think in this case there should not be like problems, but it's always better to detach things when you start doing some kind of like calculations with your vectors that are not directly tied to the loss function, because they can get away. And for example, you have some kind of calculation that should not be actually included in the loss. So probably nothing bad would happen if I remove that detach, but still it's better to leave it there. So then I also have the CPU. So I want to make sure that this moves from GPU to CPU. And then I have item. So the item works only if the tensor is one-dimensional scalar. So it's not just one-dimensional, it's just one scalar. So if inside the tensor there would be some kind of vector, so tensor would be anything, let's say 2, 3, something, whatever vector, it would not work. It would work only if the tensor is just a scalar float or integer or whatever, or the boolean. So then this item converts it back to the like just a simple Python primitive. So this will be just a float or some, yeah, I think it will be just a float. So that is the item. You can read up on that function if you're not confident with it. So here the negatives are again these things. So we can just have the opposite of the y, and then we just add them to the metrics. The metrics I print in the console, and I also make this plot so that you can see them in nice PNG images of how your training is progressing. So here the distance of the positives, append. And by the way, the deep metric learning is really interesting because that field is still changing. You can think of all sorts of interesting variations of the models, sampling methods, the loss functions. So here dist positives, dist negatives, right? So hopefully this code would be okay. I will also drop it in the Jamboard. By the way, I think I did not share the Jamboard link to everybody in the, I think it was in the event, definitely, but I will also make sure that I share the Jamboard link here in the chat in the Zoom link. Just a second. So I shared that one as well. And now let's go to the calculation of the accuracy. So to calculate the accuracy properly, what I propose is that you would run separate loop again. So of course you can calculate accuracy during the training loop or testing loop here in the where you have the like all of these loss functions and everything, but it would still be changing, so it would not be kind of fixed point of reference. So if you want to have a fixed point of reference, we should do this after the loop. So let's see where there is the loop. So this is a data loader loop. This will be train and test data loader. So if we go here on somewhere around line 189, so one thing that we can do is with torch no grad. So there is a specific function. You can also, if you look inside that function, you can see that there is also other way how you can set it, is that you don't want to accumulate any gradients. By default, PyTorch accumulates the gradients, and that makes the GPU GPU memory fill up and makes the execution slower. So that's not optimal approach. So that is one thing. The other thing is then we want to have some kind of templates. You can have also lists, but whatever. But I will make templates. So class centers. So these will be the centers of each class. Basically, again, in this case, we have the same classes in the training and tests set. That's why it will be a little bit easier here, but it's no problem to make this also work with probably with different number of the classes in the train and test set. Just need to adapt it a little bit. So this will be here. Let me think. So in the beginning, all of this will be zeros. Let me double check what was our data set. The mnist, fashion mnist. So if it's a fashion mnist, just to make the code a little bit shorter, I will just use the hard-coded number. So maybe I should at least have it here, number of classes. So it should be actually some constant number of classes. I'm just writing it here so that it is visible here. And then we have the embedding size, of course. And then if you want to operate with this on some device, so we need to send it to the GPU, to device, or in my case, if I don't have GPU, I will send it to the CPU. By the way, at any point, if you don't get it something or you have some questions, you can type in the chat, and if I don't respond, you can drop in. And I have specific way how to do this, but again, I say there are many types of methods that you can try to apply for calculation of these assignments to the classes. So my idea is that I want just to accumulate the vectors for each of the classes and then divide it by the number of instances. So I will have the centers n. So this will be just how many times I see the same sample. So there will be the num classes. Okay, this should be a shape, I think. Num classes. This will be to device like that. And then I want to go through as a loop to all of our dataset. So we will have at least 2 loops, I think, but they will be very short. So x, y in data loader, and then here will be the x to device and y to device, and here there is a trick that I told you last time, is that this default collate function of the PyTorch do not want to have just scalar values as an input for batch. So that's why I added extra dimension for each of the class indexes here. So these are actually class indexes with extra dimension. So it is in the batch, it looks something like that. So class idx1 with an extra dimension, then again the next one, and so on till the batch. And I'm now just removing that extra dimension here. Normally you should not have that, but just the way how the PyTorch collate works, That's why I kind of need that extra dimension there. So then we calculate the model forward of the x, so we get the z vector. So the z vector we then can apply using this for. So we can go to each sample. Probably you can try to write this maybe without a for loop actually, but just don't want to mess it up now. That's why I will use the for loop. So if I go to this y of I, the number rating of these samples, so then I look at the class centers yi plus zi. So I'm just accumulating all of the values of each class vectors, these embedding vectors, and also the how many times they occurred in the dataset, and then I will just divide it by them and kind of try to calculate the center of mass in that way. If I would just, so you could use probably also some median value or something like that, but if you accumulate all of those vectors as just a list, then it could eat up your memory. So that's why I'm not doing it in that way, but maybe that is beneficial. Maybe you can get higher accuracy with that. Maybe you should use then some mem maps or something. So there's other ways how to do this as well. So first of all, we have this one. Then we can have the calculate the center of the mass divided by the class centers n, but again it will not divide equally because this shape is different than this shape, and in order to divide it we need to somehow make the shapes a little bit more similar so the broadcasting would work, so we can have expansion of the dimensions inside here. So basically what it means is that this center n, before the shape was, as you see up here, number of the classes, now it will be just number of the classes, comma 1. It don't change the data, it just adds an extra dimension, that's it. So that one. So we have this one, and next there is an optional, so let's say optional L2 norm. So because all of the vectors are actually projected to this spherical space, it would be beneficial probably to also project this center of the mass. So to project the center of the mass, we could calculate the norm, so the L2 norm. By the way, I read in, I think, LeCun's paper I mentioned last time that I think in the earliest papers they use L1 norm and they have some kind of mathematical proof that this is better, but I not really not looked into that. So the class, okay, actually I don't need a dash here, so just the class centers of the norm, P2 dimensions over 1, because the first dimension is batch and we want to normalize across the features dimension. And then if we use the keep dim, it will just ensure that we can divide it more easily with the existing class center. So if I just then divide it by the norm, divided by the norm, so we now project them on the spherical space. So now we have the center of the mass is ready. So and we're just missing the last piece of calculating the closest center of the mass for each of the vectors, and then that's how we assign which class it belongs to. So again, this method is not perfect. This is just one of the simplest methods, but in general, if the loss function optimizes the distances, it's not always the worst way how to estimate it. So here there is a for of x, y. Again, we can basically copy probably these lines. So we can copy again all of these lines, I think also even these lines. So all of these, I think 5 lines we can copy. So I know it's not nice that we need to run multiple times these data sets, but in that way we make more consistent results. If we just use one loop, it kind of works, but it will not be consistent results. It will change over the training procedures. So that's why I use this method. And then if we calculate accuracy, so this will be our accuracy. and we can calculate then the distances. So this will be hopefully quite fun. So we have the distances of again basically the same function that I used last time above. This is Euclidean distances, torsion and functional pairwise distances. They have also the cosine similarity, I think, so you can use that logic that I showed you before. So if you want to move to the cosine similarity, so then expand. So the expand is like repeat basically, but just using the pointers in the memory. So I just want to make sure that the z vectors here are the same size as the center of the class. So if I use this size, maybe I should just drop in enter so it's in multiple lines. So now I'm calculating with regards to every z vector, what is the closest center of the mass. So class center, so which center of the class is the center? So and then P2. So this will be the Euclidean if this is a P2. So okay, that's great. Then very easy way to calculate the assignment is prim I, and we just use the argmin. So torch argmin like that. And this should be calculated out of the distances, right? Like that. So if we calculate like that, it should be fine. So I dropped, let me check what I dropped in the, yeah, so I dropped in this part in the Jamboard. So in Jamboard number 4 slide, I have already part of this code. So I promise we don't have a lot of code left. It's really a few lines left. So now we calculate the minimal distance for the where we have this class with the center. So that is what we know, and we already know the yi here, so that's great. So then we can calculate the accuracy append. So this will be for each batch, accuracy append of the y. So this is really nice syntax. I think I showed you also for the classification example, where you can have the boolean converted to the scalar using the multiplication by scalar. And afterwards we just add it to our total list. So this will be the metrics epoch stage. So the stage is either train or test stage we have, right? But of course it can be in inference. You could use the same procedure. So if you have the enrollment samples and some unknown samples, sorry for my language problems. So then you can use the same procedure basically. So, but here we are the training and testing. So accuracy and append. So this is a list there. It should be a list. Hopefully I don't have bug here. Yep. And in this list, I want to use again the syntax that I showed you before, torch. So actually, this is a list of those guys. Y prim vectors, where this is gonna be where it matches. And now we can calculate probably torch mean of that torch. So, but this is a list, so we need to stack it. So basically this is the last line probably. Stack it, and then we need to call the item, because then we want to make it as a float. Okay, and if it works, then I will also drop it in the Jamboard, and basically that should be it for calculating the easiest way of accuracy using deep metric learning. Let's see if I run it. Just sorry for interruption here. Running. At least I don't have errors yet. So, okay, training on CPU. I will later check that also on GPU and add the plots of the results, so it will be more fun for you. But at least my students, I will definitely require to implement more advanced methods. So the accuracy is n, so this is not what I expect, but actually maybe this is what I expect, because it's n probably because the class number of classes is not reaching what we need because of that limitation up here. Just a second, I will drop that in the Jamboard as well. So I have the max length, how this is gonna work. Yeah, so it's just cutting the samples without any... Okay, great. So Christopher is saying in the chat that it works, so that's great. So nice confirmation. So as you already can imagine, so the homework for my guys will be, and girls, will be to calculate this stuff for different ways, like for example with the cosine distance and with the clustering. So, and we'll do something of that also next time. Okay, so that's it from my part of the tutorial, and I'm very happy today that we also have on board the Bruno showing the C types.